Okay, so the YouTube link is there in the chat. Those who want can access it. Okay, so we were looking at week 3 and we will be continuing with that. So what are the things we have seen in week 3 so far? In week 3, first we introduced what are vector spaces, right? So for vector spaces, what are the main things we need? We first saw that we need an addition operation, we need scalar multiplication, and the given set should be closed with respect to this vector addition and scalar multiplication, right? And then we saw that here you can note that the first 4 properties are with respect to vector addition. So the first 4 properties here, these are with respect to vector addition, right? And then these properties, these two with respect to scalar multiplication. All right. And these two are distributive properties, combination of vector addition and scalar multiplication. So distributive properties. So distributive properties. Okay. So we have all the 8 axioms. So before that, we first have to make sure that the set is first of all closed under vector addition and scalar multiplication. So if all these conditions are satisfied, then we call such a set to be a vector space, right? And we saw some examples and non-examples of a vector space, right? And the next thing we saw is what are called the subspaces. So these are some familiar examples of vector spaces we have seen, right? And the next important thing we saw what is called the subspaces. What are subspaces? They are non-empty subsets of the vector space, right? Which are also closed under addition and scalar multiplication defined in V. What does that mean? So first of all, W is a non-empty subset of V, right? And it follows these two conditions. Take any two vectors from this subset W, then the sum is also in W. And take any scalar and a vector from W, then their scalar multiplication is also in W. So if this condition is satisfied, well, then we call W to be a subspace of V, right? And what are always given a subspace? It has two trivial subspaces, the whole space and the zero space, right? These are the trivial subspaces. So here is the GeoGebra visualization for the 2D and 3D cases. Those who want can just check it out. Okay, so in subspaces, can you tell some examples? At least we have covered the subspaces of R2. Can you recall the subspaces of R2, anyone? What are all the possible subspaces of R2?
Line.
If you just say line,
Line.
it will not be correct. You have to be precise when talking about line. Yes, line which passes through origin and
Yes, line passes through
the
and
trivial
entire
space.
plane.
Zero and the whole space. Yeah, correct. All right. Yeah, so these are the only possibilities for subspaces of R2. So since we did not cover any examples for matrix case or R3, I have just included few, just one for each case here. Okay, so maybe in the TA sessions, I will tell them to cover more examples for subspaces. All right, fine. So in the TA session, I hope the subspaces part is already covered. Yes or no? In the first TA session, is it over for week 3 or not?
No, only vector part is discussed. Subspace part is
All
still.
right, then no worries. I will tell the TA to address more problems on subspaces. All right, so here we will see some specific example for a matrix and in R3, right? So here is the question. Check whether the set W of 2 by 2 invertible matrices with real entries with the usual addition and scalar multiplication is a subspace of M 2 by 2 of R or not. Okay. So what is the given set? First of all, your given set W is nothing but the set of all matrix in M 2 by 2 of R such that A is invertible. So if A is invertible, what are all the equivalent conditions you have?
Determinant not equal to
Determinant not
0.
be zero.
right? So this is the main condition we need. Okay, so let us see with some simple examples. So let us consider the matrix A1 is equal to 1001. There is a specific name for this matrix. Can anyone tell?
Identity matrix.
Identity.
Exactly. This is
Identity matrix.
identity 2 by 2 identity matrix. All right. Is this invertible or not?
Yes, ma'am, invertible.
Invertible.
Yes,
Invertible,
ma'am, it
right?
is.
It means it belongs to W. Now let us consider this matrix. Now is this matrix invertible?
Yes, ma'am.
Yes.
Yes. So this also belongs to W, right? So here the determinant of A is 1, so which is non-zero. And here also A1. And here determinant of A2 is minus, again plus 1 only. Again it is non-zero. So these two, A1 and A2 belong to W. Now what is A1 plus A2?
Zero matrix.
It is not invertible.
So you see that A1 plus A2 is 0, 0, 0, 0. And this does not belong to W because determinant of A1 plus A2 is 0,
Zero.
0.
right? So you see that this set W is not closed under addition. So can this be a subspace?
No.
No.
So W is not a subspace. Okay, this example is clear to everyone.
Ma'am, I want to ask one thing.
Yes, ma'am.
Uh,
Addition,
what is?
right?
Sorry, your voice is not clear. Can you please repeat your question?
Yeah, ma'am, I'm asking like this subspace is what called vector. This one, vector
Sorry.
space.
Vector space is the whole space. So here your vector space is M2 by 2 of R. This is your vector space. Okay,
This
and
one.
your sorry, your voice is breaking. Maybe you can write your question in the chat.
Ma'am, I'm
Ma'am,
audible.
ma'am, am I audible now?
Yes.
I'm asking that this W is not a subspace. It is not a vector space.
If it is not a subspace, then it cannot be a vector space also.
Okay, okay, understood. That means
Ma'am,
subspace is
can you
a subset of
explain what is the
vector space.
subspace?
What is vector space?
No, I'm asking
Ma'am,
this subspace is a subset of vector space.
Subspace is a subset of a vector space which satisfies the two conditions given here. Yes.
Okay, ma'am. Okay, understood, ma'am.
Okay. There was some other question, I guess.
ma'am, can you define what is the difference between subspace and vector space?
Subspace and vector space.
Yeah.
Okay. So what is the difference between subset and a set? That is clear, right? So V is a bigger set and W is maybe equal to the set or it is a smaller set. That is, first of all, the primary difference. It is a subset of V. Okay. So for example, here itself you can see that this is a bigger set. M2 by 2 of R is a bigger set. And we are considering a subset. But in this case, anyway, this is not a subspace. Now, for example, if you take R2, R2 is your V. And if I am taking W to be set of all x comma x, where x is in R. Now, this is a subset of V which satisfies this condition. Okay, so every subspace is a vector space that is there, but anyway you see that given a vector space, a subspace is something which is contained inside the vector space and it follows the same vector addition and scalar multiplication as that of V. Is that fine?
Yes, ma'am. Can I say, ma'am, every vector space is not a subspace and every subspace is a vector space?
No, every vector space V itself is a subspace of V. Okay,
Okay.
fine, fine. All right. And
What did she say?
Why did you say it was wrong? What was her statement?
Her statement was that every vector space is not a subspace, but subspace is a vector space. But it is true in both ways. Every vector space is also a subspace, right?
Yes, ma'am.
Yeah.
So, madam, if like vector is a subspace of
Mhm.
the vector space, so is it not required to check the conditions that is we check for
The
the
whole
vector space?
space, see, the whole space, vector space already satisfies closure under vector addition and closure under scalar multiplication. So those are the conditions required for subspace. So there is nothing to check for a vector space itself to be a subspace, right?
Yeah. Okay. Yes.
All right. Now, show that the plane is not a vector subspace of R3 with respect to usual addition and scalar multiplication. Before trying to answer the question, I want you all to think about a similar scenario in R2. In R2, what are the non-trivial subspaces?
The origin.
Any line non-trivial,
The line not passing through the origin.
a line that passing through the origin, right? So what happens to the line which do not pass through the origin? What is primarily missing there in that line?
0.
The origin,
Zero.
Origin is not there.
Origin is not.
right? So now the same you should think for planes in R3 also. Lines in R3 as well as planes in R3 exactly follows the same concept. Now, without even verifying, can you tell is it a subspace or not?
No, ma'am.
No,
No.
Why not?
because 0 is not.
Origin is not.
Not
Addition is not.
a question.
So first thing to note is that 0, 0, 0 does not belong to, here it is usual addition and scalar multiplication. So we know that this is a 0 vector and this does not belong to W. So this means that W is not a subspace. So can anyone tell me how does this guarantee that W is not a subspace? The non-existence of the 0 vector guarantees that W is not a subspace. How, what logic behind is there? So this is the definition. This is the definition. But what is the logic behind this?
It is not a vector space.
Ma'am, scalar multiplication will fail here.
See, what is the logic behind this? I'm asking. So you have to tell me like which condition will fail. Because if one of this condition will fail, then only we will say that it is not a subspace. How can you say that one of the condition will fail? From this,
It is under closed addition.
how?
Hello.
If you will add x, like some put real number in the place of x, y, z, and if you will add, you will see.
So the negative v plus minus v
One
equal to 0.
In every
exactly,
cases.
exactly. That's
Yes.
the reason, right?
Yes.
So
Yes.
those who did not know, you should make it as a note here. So if here this 0 means the additive identity, remember that additive identity of V. Okay. If 0 does not belong to W, then W cannot be a subspace of V. Okay. So here let us assume that W is non-empty and W is a subset of V and 0 is the additive identity and it is not there in W, then W cannot be a subspace of V. Why is that so? Because if we take any element V in W, then V minus V should also be in W, which is the 0 vector, right? But if this is not working here, the 0 is not there, it means it cannot work. So that is why we say that W cannot be a subspace if the origin is missing. That is, the 0 vector is missing. All right. This is some shortcut which you can use in many scenario. Okay, even in this case. The 0 matrix does not belong to the set, so you can say that this is not a subspace.
Ma'am, can you repeat?
So whenever you note that the 0 vector does not belong to the subset, then that subset cannot be a subspace. All right. Okay. So for example, the same scenario happens here also. Note the zero matrix does not belong to W. Hence, W is not a subspace. Straight away, you can argue like this.
So, ma'am, any subspace will be subset of vector space only. It has a property of zero.
Any subset, sorry, what?
Any subspace, basically like W subspace, will be only when any vector will be a subspace when it belongs to when zeroth element belongs to the subspace. Basically, if you exclude the zeroth element, then it will be not a subspace anymore.
It cannot be. Yes, every subspace should contain the zero vector. Otherwise, it cannot be a subspace.
Okay, madam. But how we use this concept in the example, ma'am? X plus y plus j is equal to 1.
Here you see that 0, 0, 0. What is the sum of this vector? Sum of the components of the vector. It is 0 and not 1. So this set contains only vectors for whose sum is equal to 1. So 0, 0 does not belong to W. So if the 0 vector is not in W, then W is not a subspace. All right.
Ma'am, multiplication rule will valid here in the scalar multiplication.
Ma'am.
Scalar multiplication. You are asking whether it is closed under scalar multiplication or not.
Yes, ma'am.
See, it will fail both the conditions. For example, let us say I am going to take 1, 0, 0. Okay. So this
Yes, ma'am.
belongs to your W. So let us call this maybe V1 and V2 is 0, 1, 0. And this also belongs to W. Now what about V1 plus V2?
1, comma 1, comma
So
0.
does this belong to W?
No, ma'am.
So this means that W is
Is
not
not
closed under,
addition.
yeah, right? Same way you can say that let us take this vector 1, 0, 0. Okay, I am going to multiply it with 2. So 2 times of 0, 0, 0. This does not belong to W, right?
Yes, ma'am. Ma'am, we cannot multiply with 0 and can say.
Multiplying with 0, if it helps us to argue this, then you can say that yes, you can multiply with 0 and say that this vector does not belong to W. Yes, you can use that argument as well.
Okay.
Not
Ma'am, in
closed.
this, how we are exactly using the closed under multiplication thing? Would you
Yes.
mind explaining? Yeah.
Okay, so here we have seen either you can use any one of this is sufficient. This, either this method, or you can use this point, or you can use this point. Any one is sufficient to say that W is not a subspace.
Ma'am,
Ma'am.
can you please explain second method again?
This one.
Yes.
See, this is very simple. We are trying to see whether this set is closed under addition or not. So I have taken two elements here which belong to W. Their sum, you see their sum is 1 comma 1 comma 0. What is the sum of the elements of this vector? 1 plus 1 plus 0 is 2. But I want the sum to be 1. So this vector cannot be in W.
Even in the
Okay.
multiplication case, also we'll want the sum to be one only, right?
Exactly.
That's why since it's already 200, so it will give a sum of two. That's why it does not belong to the sub the.
Correct. Correct. Okay.
And
Fine.
one question.
Yeah.
Like in the question, in the place of 1, if you write 0, then it is a subspace or
Yes.
not?
Correct. See, that is what I'm going to tell next. See, what are the subspaces of R2? We have seen, we saw the zero subspace in R2 and lines passing through origin and the entire space R2. That is what we saw in R2. Now for R3, exactly the same things are going to come in addition to planes passing through origin. So planes passing through origin, how do you identify? AX plus BY plus CZ is 0. Right? So these are the planes passing through origin. So in this case, if x plus y plus z is equal to 0, then it is of this form. So it means it is a plane passing through origin. So it will be a subspace, obviously. All right.
Okay, ma'am.
Fine. So for just like for R2, what are all the subspaces? What are the subspaces of R3? That also you all should know by heart. So these are the only possibilities for subspaces of R3. All right. Okay. So now we will move to the next topic, which is linear combination. Okay. So what are the two operations we know so far with vectors? One is vector addition, other one is scalar multiplication. So only these two are what we know. Linear combination is nothing but a combination of vector addition and scalar multiplication. That's all. So for example, let us say you are having the vector x1. What is the vector x1? Can you tell me? X1 is
2 comma minus 2 comma 2.
no, no, no. This blue dot is your x1.
Okay, max.
Mine.
One, one, one.
2
minus
comma
1,
minus
Minus
1.
1 comma 1.
Minus 1 comma 1, right? Same way, this green dot is your x2. What is your x2?
2 comma 1.
2 comma 1, right? So x1 is minus 1 comma 1 and x2 is 2 comma 1. Now let us try to do scalar multiplication to this. Then what will happen? So let us say your c1 is 2. So c1 times of x1 means you will get, so
Minus 2.
c1 x1,
Minus 2 comma 2.
yeah, minus 2 comma 2. So it is this point. Same way, c2 times x2 means 3 times of 2 comma 1. So you get this point, which is 6 comma 3, right? So this is scalar multiplication. This we already know. Then what else we know? We know sum of two vectors x1 plus x2. Or we can also find the sum of c1 x1 and c2 x2, right? So here we are trying to find the sum of c1 x1 and c2 x2. Now we know this is c1 x1 and this is c2 x2. What is their sum?
Minus 264 comma 5
5,
is
right? So the resulting vector is 4 comma 5. So there is nothing new we have done here. So first we did scalar multiplication and then we added the scalar multiplied vectors. This is linear combination, that's all, right? There is nothing new in linear combination. Instead of simply adding the vectors, we are adding the scalar multiplied vectors. That is linear combination. So linear combination of what? So this is a linear combination of x1 and x2. So what is this? This is a linear combination of x1 and x2. Okay. But is there any significance about this specific C1 and C2 for this linear combination? If we change C1 and C2, will that C1 x1 plus C2 x2 will be still linear combination of x1 x2? Yes.
Yes, madam.
yes, ma'am.
Okay.
Yeah.
What is the definition of linear combination? First, I will tell you the definition of linear combination of one vector. What can you tell me? What is a linear combination of one vector?
Multiplied by some scalar.
Just a scalar multiple, right? Now, linear combination of two vectors means scalar times first vector plus scalar times second vector. That is linear combination of two vectors. Now, what is the linear combination of n vectors? It is nothing but,
Scalar multiple of n vector
yes,
and
so
then some.
a1 v1, a2 v2 up to an vn, right? So this is the linear combination of n vectors. That's all. Okay. So is it clear what is a linear combination? Is it clear for everyone? Okay.
Ma'am,
Okay.
what we achieve
Ma'am,
through
what you have said, I have written that a scalar multiply scale adding scalar multiplied vectors.
Yeah.
Yes,
That,
ma'am.
yeah.
Ma'am, the resultant vector here,
Mm-hmm.
the C1 x1 plus C2 x2, they will be lie in the same plane, whatever we use the scalar.
Exactly. Exactly. Because of the
And it,
parallelogram law. Yeah.
mm, and it will be true for the n vectors also, ma'am.
Yes.
Okay, okay, ma'am.
So
Yes,
for
thank you, ma'am.
n vectors, it is, see, it
Mhm.
depends on where your space is and what kind of vectors you are taking. So for that, you need some more concepts to explain where this linear combination will lie. So for that, you need the concept of span to understand where the sum of the n vectors are going to lie. Okay, so maybe we will
Okay, ma'am.
check this concept when we learn about span. Okay, so his question
Yes,
was
ma'am.
that where this vector will lie. So for that, I'm saying that the answer you will get when you read about span of vectors. Okay, maybe in the next week. All right. So
Ma'am,
Just
just one question. Why we multiplying the scalar here? Reason behind it.
okay. So why we multiply?
Yeah.
Okay, and I'll tell you.
Yeah.
Uh, I will not tell you the exact answer. The exact answer you will get after few slides itself, but I will give you a hint of what are we trying to do. See,
Yes. Yes.
now R2, how many points are even R, let us take. In R, how many points are there?
No.
Infinitely many.
Infinite.
So many are there. What about R3?
Same. Infinitely
So,
many.
so many points are there. You take
Yeah.
matrix spaces, again, so many points are there. Okay? So now the spaces are huge. How are we going to study these huge spaces? Okay, so if we have like just like taking an example of a classroom, so the teacher, what does the teacher usually does in a classroom? So there are so many students in a class, so instead of monitoring every student, the teacher has some students who can take care of the other students, right? Like class monitor they call. The
Yeah.
same thing we are doing. So we are having a huge space. Instead of just considering all the points in the space, we have some specific special set of vectors which can help us to take care of all the vectors that can be achieved through this linear combination.
Okay, ma'am.
Okay, so
Okay.
I'll tell you that I can explain you more after a few slides. All right?
Just one follow-up question, ma'am.
Yes,
Just yeah,
yes.
we cannot achieve through this actual vector. Like we have initially the vector is a one comma minus one comma one,
Mm-hmm.
and two comma one.
Yes,
We can also achieve from this point or not.
yes, we can. From these two vectors, we can actually express any vector from this whole R2 using these two vectors.
Yeah.
Okay, that we will see soon. Okay,
Okay. Okay, ma'am. Thank you.
fine. Okay, fine. So before answering further questions, I will try to explain few examples and then I'll answer if there are any other questions. I'll answer after that. Okay. So now let us consider these two vectors. These two vectors are very special and we will use this vector very frequently from now on. What is this called? These are the unit vectors along x-axis and y-axis, and this is usually called as the standard. We have not yet introduced basis, but anyway, I think this is called a standard basis. Okay, so 1001. Okay, 1001. So it is this vector here. You can see 1001, the unit vector along x-axis and y-axis. Okay, so now what is the significance of this vector? Okay, let us take a vector, any vector. Let us say, for example, minus 2 comma 3. Is it possible to write this vector minus 2 comma 3 as a linear combination of v1 and v2? What's your answer? So
Yes,
Yes,
ma'am.
ma'am.
so
Yes, ma'am.
Yes, ma'am.
what are the scalars c1 and c2?
Minus 2 and
Minus
3.
2 times.
Minus 2 and 3. Right? It is very straightforward that this minus 2 and 3 we can easily find out, right? So did everyone understand how we got this minus 2 and 3 here? Yeah?
Yes, ma'am.
Yes,
Right?
ma'am.
Now, instead of this, I'm taking the generic vector x comma y. Now, what is your c1 and v1?
X and Y.
x into 1 comma 0 plus y into 0 comma 1.
So you can see that any vector, any arbitrary vector in R2, I am able to express it as a linear combination of these two vectors. Right? So these two vectors are sufficient to write any vector as a linear combination. Right? So now let us try here. Can we write this v equal to 5 comma 6 as a linear combination of v1 and v2? So you have c1 times of 1 comma 2 plus c2 times of 1 comma 1. If we rewrite c1 plus c2 comma 2c1 plus c2, and on the left hand side we are having 5 comma 6. So what are we getting from here? We are getting a system of equations. c1 plus c2 is equal to 5 and 2c1 plus c2 is equal to 6. Can you quickly solve this system and tell me the answer?
Ma'am,
Yes.
C1 is 1 and C2 is 4.
Okay, let us check. So C1 is 1 and C2 is 4, right?
4.
Okay, let us check whether it is correct or not. Okay, so if I put C1 equal to 1, so the first vector I am getting, so C1 times V1 is 1 comma 2 and C2 times V2 is 4 comma 4. And what is C1 V1 plus C2 V2? 5 comma
5,6.
6. So this answer is correct. Okay, so what is the beauty of this vector here? We were writing this vector as a linear combination of V1 and V2. The C1 and C2 you told without any calculation. You were able to tell the answer straight away, right? So this is the beauty of this vector, and that is why for the simplicity of the calculation purpose here, we use this in many scenario. Okay, this also does the same thing here, but here some calculations are needed. We cannot just by looking at it we cannot tell it. Okay, but this also does the same job like this set of vectors v1 and v2. So here given a vector, we are able to write it as a linear combination of these two vectors. All right. Okay, now maybe this I can leave it as a homework. 3 comma 2, check whether you are able to write it as c1 v1 and c2 v2. Find c1 and c2. Okay, fine. Okay, note that if v1 and v2 are non-zero vectors, all these three are non-zero vectors, such that v is equal to a1 v1 plus a2 v2 equal to plus a2 v2, where a1 is non-zero and a2 is non-zero, then each of the vector is a linear combination of the other two vectors. First of all, everyone read this statement again and see whether you are able to understand. If not, you can ask me, I'll explain. Read the statement carefully. Yes, do you understand?
Yes, ma'am.
Yes, ma'am.
Yes,
So,
ma'am.
so from the given expression, what we can say, V is a linear combination of which vectors?
V1 and V2.
V1 and
V1 and V2. Now suppose,
Ma'am,
yes,
ma'am,
yes.
ma'am, can this coefficient be 0?
If it is 0, there is a problem in saying this statement. Why? I will tell you now. See, V is equal to A1 V1 plus A2 V2 helps us to tell that V is a linear combination of V1 and V2. First, let me complete the explanation for this and then I'll answer your question. Now, V is equal. Now, for the next one, what should be the expression which we need? We need V1 to be a, because I'm saying each vector is a linear combination of the other two vectors. So it means what? I can write V1 as a linear combination of V and V2. How can that be achieved? Yes? Those who said you understood, tell me. How can this be achieved? This is comma here, by the way. Don't think it as V1.
I'm subtracting.
And V minus A2 V2.
Yes. So you
V
can
minus
write.
A2 into by A1.
Yes, yes. So you see that V is equal to A1 V1 plus A2 V2. So from here, we can rewrite the expression and write A1 V1 equal to V minus A2 V2. Now, since this A1 is non-zero, the one who asked me what will happen if A1 is 0. Since A1 is non-zero, I can divide it on both sides and I can write V1 as a linear combination of V and V2. So the same can be done for V2 also, right? V2 can be written as a linear combination of V and V1, right? So the expression is V2 is equal to V1 by A2 minus A1 by A2 V1. That's all. Right? So here again A2 is non-zero, hence I am able to do this. So if I am having V is equal to, suppose A1 is 0, then I will simply have A is equal to A2 V2. So it means V is simply a linear combination of V2 I can see from here. So writing V1 as a linear combination of V1 and V2, we don't know. Okay, fine. So From here up to this, are you all following? Yeah.
Yes, sir.
Yes, ma'am.
Okay, fine. So now a few more things which you should have like observed. So further zero can be written as a linear combination of v1 and v2. What is said here? Each vector is a linear combination of other two vectors. The one more thing from the same statement, we can achieve that zero can be written as a linear combination of v1 and v2. How is that?
Yeah, we'll take all the elements left side.
Ma'am, can you
Yes.
please the
Other
All
side
the
will be
combinations.
So we take everything to one side. So a1 v1 plus a2 v2 minus v is equal to 0. So in that case, here your coefficient is minus 1. Here the coefficient are a1 and a2. There is one more way to write these vectors as a linear combination of 0. What is that?
0v1, 0v2
Yeah,
is equal to 0.
right? Okay, fine. So these are just some simple observations. That's all. Nothing much in these places. Some observation. That's all. Okay. Now v1, v2, v3. In R3, now we are considering these vectors. Does this look similar to some example which we saw earlier?
Yes, ma'am.
Right? So this looks similar to this set of vectors from R2. Right? Again, this is a standard basis we say for R3. Right? Now, any vector in R3, can we write it as a linear combination of V1, V2, V3?
Yes, ma'am.
The same concept, right? So X V1, Y V2 and Z V3. Is this correct?
Yes, ma'am.
Fine. Okay. So now you have three vectors here. Now from R3. So whatever we did in R2, the same calculation only we have to do here. So now V is equal to 3, 7, 2. Can we write this as a linear combination of V1 and V2? Quickly check and tell me. I don't want to spend time for calculation here. So I'll give the answer here because let's not waste time for just some simple calculation. So C1 is equal to 2 and C2 is equal to 3 by 2. So maybe you can simply verify whether it works or not. So this is the answer, right? Okay. Now the plane that contains these 2 points is given by, so this is given to you. For now, let us just see that this is the plane which is containing these 2 points. How can we check this statement that this plane contains these 2 points? How can we check?
put the points and check.
We just put the value of xyz in the equation.
So 2 times of 0 minus 2 times of 2 plus 4 times of 1. What is that?
0.
Yeah, it is 0. Same way you can check for this vector also, right? It also belongs to this plane. Okay. Now the question is, let V be any linear combination of the vectors v1 and v2. Okay. So it means what? V is some c1 v1 plus c2 v2. Now, does V lie in the plane containing v1 and v2? What is your answer?
Yes, ma'am.
Yes.
Okay. How can we check that?
Just simply by putting the values, we can also check that as we check the above point, ma'am.
Right? So you can see that just by simply substituting this, you can do this. How can we do this? 2 times of C1 V1 minus, maybe I should write what is V1 and V2, then only we can do this. Otherwise, it does not make sense. So V1 is equal to, let us say, X1, Y1 and Z1. And V2 is equal to X2, Y2 and Z2. Now we can do that. So now C1 V1 is nothing but C1 X1, C1 X2, Y1 and C1 Z1. Right? So now we can do that 2 times of C1 X1, here I need plus C2 X2, right? Plus C2 X2 minus 2 times of C1 Y1 plus C2 Y2 plus 4 times of C1 Z1 plus C2 Z2. What is this? This we know that it is nothing but C1 times 2x1 minus 2y1 plus 4z1 and C2 times of 2x2 minus 2y2 plus 4z2, right? We already know that v1 and v2 are vectors in this plane. So this satisfies 2x1 minus 2y1 plus 4z1 is 0, and this satisfies the same condition, right? So if these two are satisfying here and we substitute the values here, we get that this value is also 0. This means what? This vector, what is this vector we have used here? So v,
V.
your v also belongs to the plane. Okay, so what is that we have seen here? If there are two vectors which are lying in a plane, then the linear combination of those vectors also lie in the same plane. So this is the argument we see for that. So instead of 2x minus 2y plus 4z, if we have any plane of the form ax plus by plus cz, you are going to apply the exact similar steps for understanding that any 2 point lying on this plane is going to lie, the sum is also going to lie on the same plane. Is that clear? Yeah.
Yes, ma'am.
Yes, ma'am.
Yes.
Okay, fine. So the next question is that let w equal to 1 2 0, does this vector belong to this plane?
No.
Okay, so you check 2 times of 1 minus 2
No,
times
ma'am.
of 2 plus 4 times of 0. Is that it is 2 minus 4 plus 0 minus 2. So it is not 0. So it means this point W does not lie in the plane 2x minus 2y plus
Yes.
4z is equal to 0. Okay, it does not lie. Okay, now there is a follow-up question. Can we write W as a linear combination of V1 and V2? Now W, we see that it does not lie in the plane. Can we write W as a linear combination of V1 and V2? What is your answer?
No.
No.
What does that mean? So if we consider the equation C1 V1 plus C2 V2 is equal to 1 comma 2 comma 0. See, we cannot find the C1 and C2. It means the system of linear equation which we can obtain from this will not have a solution. That is what you can obtain from here. Maybe you can check it as a homework that this system has no solution.
Ma'am, may I know how do we find the equation of the plane?
How do we find the equation of the plane?
Putting x1 there, ma'am. 2x1.
See, you are asking from these two vectors how to find the plane containing these 2 points. Is that what you are asking?
Yes, ma'am. The equation of the plane, yes.
That there is one non-algebraic method, I guess you used in the analytical geometry. So I guess you use cross product and find it. That is one way. But here in this course, when you look at the concept of span, you will see how to find this plane. Okay.
Okay, ma'am.
Okay. Can we write 0 as a linear combination of these vectors? Of course, we can write in one way with that you know. What is that one way?
0 multiplied by both the vectors.
Right.
Okay. But what about a non-zero solution? How do you know whether there is a non-zero solution or not?
We'll have to take to take different coefficients and then check
Yes.
this.
So here let us see what is the scenario here. Okay. So let us consider C1 V1 plus C2 V2 plus C3 W is equal to 0. See, now we know that V1 and V2 are from this plane, and W is a point which is something outside from the plane. Now we want to see what is the solution of this equation. Now let us first rewrite the equation. So C1 times 0 comma 2 comma 1 plus C2 times 2 comma 2 comma 0 plus C3 times 1 comma 2 comma 0 is equal to 0. Now what is the system we obtain from here? This is 0. So you simply get 2C2 plus C3 equal to 0. And then 2C1
Plus 2C2.
Yeah. 2C1 plus 2C2 and here it is
plus
0.
2c3.
Oh, yeah, plus 2c3. The next value only is 0.
Yes,
0.
ma'am.
And then you have c1
C1.
is equal to 0.
Zero.
So if c1 is 0, what will happen to this equation?
2c2, 2c3 is equal to 0.
Right? Now, c2 plus c2
C2.
plus 2c3. Can I write it in this way? 2c2, I'm just splitting it into c2 plus c2.
Yes, ma'am.
Yes,
Now,
ma'am.
this part is already 0.
Mm-hmm.
Oh, I have to split c3, not c2. Sorry. So 2c2 plus,
C3.
Plus E3 plus E3.
yeah. So now
Yes,
we see
C3 is
that,
equal to 0.
yeah. So the first part is 0. So that implies that C3 is 0. So if C3 is 0, automatically C2 is also 0. So what we can observe is that the only solution for this system we can see is that C1, C2, C3 is equal to 0. What is the significance of such a set? We will see soon. Okay, so for now, let us keep this example. Okay, so what is that we have noticed? We have taken two vectors from a plane and one
Madam,
vector. Yes,
can you please repeat the what is the significance of this?
what is the significance of this? I have not yet told. I have
Okay,
just
okay. Sorry,
I
sorry.
told the process. We'll see now. Okay, the significance we'll see. Okay. So before even looking at, okay, there is one exercise, and after that, maybe I will start giving you some intuition to understand the significance. Okay, quickly, everyone, try to solve this problem. Try to do it yourself, everyone. So this is the equation which you should consider to solve the problem.
x1 1 x1 1 minus 1.
Okay, so x is 1, y is 1, z is minus.
Minus
So what is x plus y plus 2z?
0.
Yeah. So how many of you were able to complete it? Yeah. Maybe a thumbs up, those who are completed. Okay, fine. Only few thumbs up I can see. Okay, some more are doing. Okay, fine, good. Okay, so just some quick intuition I will tell you. Okay, so let us consider R2. Okay, so let us consider some point in R2. Maybe let us consider this point. What is this point? Can you tell?
1, 2.
1, 2.
1, 2. Okay, so I'll just put this so that I can put this point as well. So now what is this point here?
2, 4.
4.
2, 4. Okay, so this you can note that. What is that you can note? Both are on the same line,
Scalar.
right? One is a scalar multiple of the other. You can note that. Let us say this as your u and this as your v. Then you can see that your v is 2 times of u. Or you can say u is 1 by 2 times of v. Either way, what is that you can see is that u and v lie on the same line. Geometrically, they lie on the same line. And when you look at the values, you can see that one is a scalar multiple of the other. Okay. So v is a scalar multiple, or you can also say linear combination of u, right?
Yes, ma'am.
Yes.
Scalar multiple or linear combination of u. Okay. So now can we obtain 2, 4 from 1, 2?
Yes, ma'am.
Yes, it can be obtained
multiplied
by
by 2.
substituting 2 times of 1 comma 2. So 2 comma 4 can be obtained from 1 comma 2, and same way 1 comma 2 can be obtained from 2. Sorry, 2 comma 4. This is one thing. Okay, fine. Now let us look at maybe this definition, then we will come back to this point and this part here. What are linearly dependent vectors? This is what we are going to see. So what are linearly dependent vectors? A set of vectors from a vector space is said to be linearly dependent. So this is a very abstract definition. So just look at the definition. Once you understand the intuition, you will have a clear understanding. If there exist scalars a1, a2, an, not all zero. At least not all zero means what? At least one of them should be non-zero. At
Non-zero.
least one should be non-zero. Such that this equation is satisfied. Now we have two vectors. So let us say v1 is your 1 comma 2 and v2 is your 2 comma 4. Okay. Now a1 v1 plus a2 v2 is equal to 0. What is the solution for a1 v2? Can we find a1 a2 not all 0? All 0 is one possibility. We are not going to consider that. I want to check whether we can find non-zero values for a1 and a2 to obtain this equation.
A1 we can put -2 and V2 we can put 1.
Yes, we already know that 2 times of v1 minus v2 is 0. This we already know.
Right.
So it means a1 is equal to 2 and a2 is equal to -1 gives a possibility for such a solution. So from this definition, what can we say? V1 and V2 are linearly
Linearly dependent.
dependent. So dependent means what? One is dependent on the other. Is it not obvious? One is dependent on other.
Yes.
Yes, one can be obtained from the other.
Yes,
Right?
ma'am.
So now whatever you understood here, now they are extending it for n number of vectors. So if you have n number of vectors and you consider their linear combination to be 0, then if we are able to find non-zero coefficients, at least some of them to be non-zero, then you can say that that set of vectors are linearly dependent. Okay. Now, okay, here what is given here, let us first see and then I will explain more. In other words, a set of vector is linearly independent if the zero vector can be written as a linear combination of those vectors with at least one of the coefficients being non-zero. Just the same thing explained in different words, that's all. Okay, now there is one question here. If a set is linearly dependent, then so is every superset. First of all, many students forget what is superset. How many of you remember what is a superset? Okay, no issues. It's a very simple concept. Now we say that A is a subset of B, right? And B is a superset of A. That's all. So what is a superset? You understand?
Yes, ma'am.
Yes,
A set
ma'am.
which
Yes,
contains
ma'am.
a set.
It
Okay.
contains the subsets.
Yeah. Okay. So
Containing all elements of it.
yes. So now let us say you have a set of vectors which are linearly independent. So then what is given is that every superset is also linearly dependent. Is it not very obvious? Why? So let us say I have V1, V2, Vk. This is linearly dependent. What does that mean? This means that there exist A1, A2, Ak in R where at least one AI is non-zero such that A1 V1 plus etc. AK Vk is equal to 0. Up to this, it's just the definition. Is that fine? I have just written the
Yes, ma'am.
definition. Yeah.
Yes.
So here, this many students ask, you did not ask, what is the symbol?
There exist.
Belongs to, yeah,
Belongs.
there exists.
For all.
There exist. There exist. There exist.
There.
Okay. Fine. So sometimes I just write and forget to tell. That's why. Okay, I told it now. Good. Okay. Now I'm going to add few more vectors here. Okay, even if I add one vector, it is going to be linearly dependent. The argument is very straightforward. Can you see that or not? So suppose I am going to add v1, v2, vk. I am adding, let us say, just one vector. The same logic is going to be applied for any number of vectors. Suppose I am adding one more vector. Now this new set is also linearly dependent. How?
If it is not zero.
Because there is already one
Yes, exactly.
coefficient basically, which is zero. Yes, ma'am.
Correct. See, already we have the coefficients where one of them is non-zero. So I can simply put 0 times of v equal to 0. And anyway, the coefficients, one of them is non-zero. So this set is linearly dependent. Do you all understand? So what I'm going to do is that I'm simply going to write the same expression up to vk. And for whatever vectors which are going to be added up, I will simply put 0 times of v. So the same can be done for any number of vectors. 0 times of those vectors equal to 0. And one of the coefficient is already non-zero. So this set is linearly dependent. Is that clear?
Ma'am, if the coefficient of the v is also non-zero, then it is okay now.
That is fine, but we don't know what are the vectors. So what is the coefficient we cannot find. So this easiest method to obtain 0 is just by adding a 0. This is not going to change the value of this vector. So this is the easiest option we have for the coefficient of v.
When
Right?
linear dependent vectors we're finding,
Hmm.
for what means, is there any reference to that for which we are finding the linear independent or dependent?
Yes, yes, yes. Linear dependence, independence, everything has a purpose. Okay, I'll tell you one by one. I cannot, well, while you are just studying ABCD, you don't know what are the applications of ABCD, right? So I cannot explain it to you at that point. So just wait few more minutes, I can tell you. Okay, fine.
Ma'am, can you please repeat why you put 0 as a coefficient of v?
See, whatever coefficient you can put, but the thing is that it should satisfy that it is equal to 0. That is the problem here. See, what is the coefficient here? You don't know, so that you will get 0. But 0 is a straight away answer. Yes or no? Right?
Yes.
Yes, ma'am. Yes, ma'am.
So that is why I have taken 0. Okay. So this 0 just makes us to obtain the equation to be 0 easily. That's all. No other reason. Okay. Fine. Now, okay. Let v1 and v2 be two linearly independent vectors. What does that mean? So you have a1, v1. So I can write there exist a1, a2 in R such that a1, v1 plus a2, v2 is equal to 0. So either a1 non-zero or a2 non-zero. Right? So or both of them can be non-zero. That is possible. Okay. So a1, v1 is plus a2, v2 is equal to 0. From this, what can you see? a1, v1 is equal to minus a2, v2. Yes or no? Yes or no?
Yes, ma'am.
Since one of them is non-zero, I can assume for now a1 is non-zero. So it does not matter. You can assume this or this to be non-zero. That does not matter. So let us say a1 is non-zero. Then I can write v1 as minus a2 by a1 times of v2. What does that mean? v1 is a scalar multiple of v2. Yes or no?
Yes, ma'am.
The same can be done the other way around also when I have a2 non-zero. That v2 is a scalar multiple of v1. Right? So what is that we have in general is the same thing we see in R2. When two vectors are linearly dependent, then one is a linear multiple of the other. That is what we saw in the very beginning. Right? So that is the scenario in general also. You take any vector from Rn matrix or anything. It can be from any vector space. But once you know that they are linearly dependent, then one is a scalar multiple of the other. This is a common property. Okay, so what is the observation? If two vectors are linearly dependent, then they are
In the
scalar.
same plane. Yeah,
Multiple.
scalar
Scalar
multiplication.
multiple.
Okay. In other words, they lie on the same
Plane.
line.
Plane.
Line.
Same line. line, yes,
Only
ma'am.
two vectors, and linearly dependent means they are lying on the same line. Okay, fine.
Yes.
Now let us consider three non-zero vectors in R2. Okay, if there are three non-zero vectors in R2, what will happen? Will they be linearly dependent, independent? Any guess?
Dependent.
Okay, let us see. How is that dependent? The argument, can you tell?
Ma'am, can
We,
you
we
repeat?
can describe the entire space with if two of them are independent, with those we can like V1, V2, we can express the whole space, and then V3 has to lie in those two.
Okay,
Or
fine. So yeah, that is the intuition, but yeah, you can even tell it with more mathematical stuff. That is also mathematical only, but here maybe in some we using the definition. Maybe using the definition also we can tell. Okay, let's see how to do that. Whatever you
Ma'am,
said
what
is
is your
perfectly
question?
correct.
Can you repeat?
Yes. So now you have three vectors. My question is, are these three vectors linearly dependent or not? Okay, so I'm asking whether this set V1, V2, V3, is it linearly dependent or not? Okay, so now for that it means we have to find non-zero coefficients, at least one non-zero coefficient for this expression, right? Now what is this expression? V1, V2, V3 are vectors from R2, right? So we will write V1 as x1, y1, V2 as x2, y2, and V3 as x3, y3. So it means what you have? A1 x1 plus A2 x2 plus A3 x3, comma A1 y1 plus A2 y2 plus A3 y3 is equal to 0 comma 0. Right? This is, I have just rewritten this. This step is fine, right? Yeah.
Ma'am, can I
Yes, ma'am.
see in this two variable and three equation that is it is dependent in R2?
Two, sorry.
Two variable and three equation that in R2, that's why it is dependent.
Yes, you are saying it, but not completely. You are not filling the gap in between. Yes, that is the point here. So now we are having two equations, right? So now what are the two equations? A1 x1 plus A2 x2 plus A3 x3 equal to 0. And the other equation is A1 y1 plus A2 y2 plus A3 y3 is equal to 0. Right? So the matrix you have is x1, x2, x3, y1, y2, y3, and a1, a2, a3. Right? So this is equal to 0. Now for this system, what is the size of the matrix?
2 cross 3.
So you are having a homogeneous system like this, where your m is strictly less than n. So what do you know about this kind of a system? If ax is equal to 0, where m is strictly less than n, what do you know about the solution of this system?
one
This
free
system will
variable
have
should be there.
this,
Infinite, infinite,
Infinitely many.
yes,
infinitely
this
many
have
solutions.
infinitely many solution, because you will get a free variable anyway. You will get a, okay, I have not yet taught you dependent and oh no, it's taught. So anyway, you will have a dependent variable. So automatically you will have independent variable will be there because of the free variable here. So infinitely many solution will appear here. Okay. So in this scenario, always whenever you have an m by n matrix where m is less than n, you have infinitely many solution, right? So since you are having infinitely many solution, you are going to have some non-zero solution for this equation. Yes or no?
Yes,
Yes,
ma'am.
ma'am.
Yes.
So if you are having non-zero solution, is the set linearly dependent or not?
Yes, ma'am.
Yes,
It is
ma'am.
linearly dependent, right? So the answer here is that it is linearly dependent. Okay.
Ma'am, can we find those scalars?
Sorry?
Can we find those scalars who make this linear dependent?
What is V1, V2, V3 is not given here. V1, V2, V3 are just any three non-zero vectors in R2. Only when we know what are the vectors v1, v2, v3, then only we can talk about what are a2, a3, a1, a2, a3, right? This is just some random vectors from R2. We don't know the values. If it is given, then of course we can solve the system and find it.
Okay.
Okay.
Yeah.
Ma'am, can you explain how infinitely many solution if m is less than n?
Okay. If m is less than n, what will be the RREF form? How does the RREF form will look like?
Upper triangular.
See, we are not in a square matrix case. We are in a rectangular matrix case, right? So either the RREF form is going to. There are three
There will be
possibilities.
there will be
Three
two
or
and two.
many possibilities. So you will have either 1 0 0 1 and then some values here. This is one possibility. There are several possibilities you can
Two
think of.
dependent variable and one independent variable basically.
Yeah, so you will have something like this. So anyway, you see that there is one independent variable always.
Okay, okay.
This independent variable
And
is
take
going
any
to
vector.
contribute infinitely many solution. Okay, fine.
Okay, ma'am.
Okay, so you have more things here. So everyone, there is a small exercise I'm going to give to you now. Whatever we did here, do the exact same thing when you have four vectors in R3. Okay, just write down the steps so that you understand what is going on. Just write down the step and see what will happen when there are four vectors in R3. Just do the same process. Okay, and check whether the set of vectors v1, v2, v3, v4 are linearly dependent or not.
Excuse me, ma'am.
Yes.
Ma'am, when will it have infinitely many solutions?
Why? What?
When infinitely many solution?
Mm. Infinitely many solution. What is your question? I only hear infinitely many solution. What is your question?
Ma'am, when we say that it having the infinitely many solution.
So for this particular scenario, it has, there are many other scenarios when ax is equal to b and ax equal to 0 when m greater than n also. This is one particular scenario where we have infinitely many solution. If you want all scenarios, that is a different topic. Okay. So in this scenario, you see that ax is equal to 0 and A is an m by n matrix where m is less than n. So here we have infinitely many solutions. Okay. Because of the existence of independent variable in such scenario. All right. Okay.
Yes, ma'am.
Fine. Okay, so complete this. We will continue again in 5 minutes. All right.
Okay.
Yeah, yes, ma'am.
Those who have completed 3 can try 4 also. So have you completed? Yeah? Is it done?
Yes, ma'am.
Okay. So in this case, you would have got what is the size of the matrix you obtained here?
3 cross 4,
10
madam.
plus
3 cross
4.
4.
So you would have obtained a matrix system X is equal to 0, where A is a 3 by 4 matrix. Again, this system has infinitely many solutions. So you know that there is a non-zero solution for the equation C1V1 plus C2V2 plus C3V3 plus C4V4 equal to 0. So this is linearly again dependent. So in general, what is the answer? In general, if there are n plus 1 vectors in Rn, what is that going to happen? You are going to get,
Linearly
Infinite solution.
so any n plus
Linearly
1
dependent.
vectors in Rn are
linearly dependent.
dependent. Right? Okay. Now what about this set? Is this linearly dependent?
Yes, ma'am.
Yes, ma'am.
Yes. Why?
Because zero vector is present.
Because zero vector is there, you can put any non-zero coefficient for that, right? So you can put a1 v1 plus a2 v2 plus etc ak vk. You don't know about what are the coefficients of these, it does not matter, because always you can put a scalar here, any non-zero scalar, right? So what is this notation? You all know, right? What is this notation? You all know or not? R
R
minus 0.
Real set without the element 0.
Minus 0.
So A can be any non-zero real number, right? So since we can put this, we can have that S is this set is linearly dependent. Okay, fine.
Ma'am, if it is in the place of 0, it is non-zero, then what will happen?
We cannot say. It depends on where this vectors are from. Okay, and what is your k? It depends on many things. Okay, fine. Okay, so any set containing the zero vector is
Linearly dependent.
Linearly dependent.
okay. Fine. So consider the set 1, 2, 4, 2, minus 1, 2, 5, 0, 8. Check if this set is linearly independent. How will you check? By solving the system of equations, right?
Yeah.
Yes,
Gaussian number.
Okay.
equations.
One straightforward method I will tell you instead of the method we used here. Okay. So whenever you are having, suppose there are n vectors from Rn. Okay. So what is the system you will get by considering C1, V1 plus etc. Cn, Vn is equal to 0? You are going to get a system Ax is equal to 0 where A is an n by n matrix.
Yes, ma'am. 3 cross 3 will be.
Yeah. So in this case, it is 3 cross 3. So in that case, to check whether it is linearly dependent or not, it is if enough if we check determinant of,
He is not
yeah, A is 0, right?
0. Yes.
So if determinant of A is 0, then V1, V2, Vn is linearly dependent. So now quickly tell me whether this is linearly dependent or not. How will you check? Will you check?
Calculate the determinant of matrix.
Yes. Find the determinant of the matrix.
Okay, ma'am.
Zero.
This is the system you have, and the determinant is 0.
Determinant is 0, ma'am.
So this means the set is linearly dependent. So it's called V1, V2, V3. So this is linearly dependent. Fine. Okay. Okay. So let us look at the next question. Read the question, everyone. First, try to understand.
Ma'am,
Hmm?
hello ma'am.
Yes. Yes.
Why you put the vector in column wise?
Just imagine what happens, or maybe look at the examples from here. It does not matter because determinant of A and determinant of A transpose are same, so it does not matter. But this is the equation, the system you are going to obtain. See, check from here. A1 V1 plus A2 V2 plus A3 V3 equal to 0. So you get x1 x2 x3 here, y1 y2 y3 here, right?
Yeah, got it.
Yeah. So now look at this question, everyone. Try to understand how to do this.
We can put one by one option and get the determinant in this way.
Okay, you can put determinants. Yes, that is one way of understanding. Yes, of course. Any other possible suggestions?
Trying to find the linear combination of the two.
Yes. Okay. Is there any property you can just observe?
Scalar multiplication is there. We try to
Zero in
find
the third column. 0, 0, 0.
Sorry, what is zero?
0 in the third column.
Exactly.
0 in third column. Yes, ma'am.
So if you consider any of these options, like option 2, 3, and 5, you see the third entry is 0. So if
Yes.
the third entry is 0, you will get the entire column to be
0.
0.
right? So in that case, the determinant is obviously
0.
0.
so you know that these options are correct. So now your job is only to check whether the determinant of these are 0 or non-zero. That's all,
Yes.
right? So for this, you can simply quickly verify the determinants. What are the determinants? And there is one more thing also. You can see whether you will be okay. I have not taught the span concept. Okay, maybe not. Just do the determinant concept for now. The other method maybe I'll tell later. Yes. What are the determinants, non-zero or zero for option 1 and 4?
For one, it is
4.
non-zero.
Yes, non-zero. 2 it is.
So this is non-zero. So this is incorrect. And what about option 4?
Non-zero again.
Correct.
Yes, ma'am, non-zero.
Yes, ma'am, non-zero.
Okay. So by the way, since we are doing the determinants, I just wanted you to go back to row operations, okay, and answer this question, okay, because it is going to be useful here also. That's why. So let us say you are having, this is V1, this is your V2. So is this how we are getting 1, 2, 4? Yeah, V1, V2, and suppose this is A1 V1 plus A2 V2, or it does not matter. Let us say we are having the transpose and you are having the vectors like this. That does not matter. Either like this or like this, it does not matter. Okay, it means what I'm trying to say is that let us assume one of the row is a linear combination of the other two. So when you do the row reduction, what will happen to the last row?
For linear
All
dependent, it
elements
has to
become
be
0.
Right? So the last row becomes 0. If the last row becomes 0, what is the determinant of the matrix?
Excuse me, ma'am.
Yes?
0.
Ma'am, I am unable to
Zero.
understand how third column and third row A1 V1 plus A2 V2.
No. This is a suppose condition. Okay, so I'm talking about suppose. Suppose
Okay,
this
ma'am.
is a scenario. Okay, suppose this is a scenario. Okay, so now if this is a scenario, you know that the RREF form, or even simply the REF itself, we don't even need RREF. The REF form will have 000 here. Yes or no? Here some entries are there. That does not matter for us.
Yeah.
But the last row will become 0. True or not? After
True.
row
Yes,
reduction.
Yes.
ma'am.
Yes.
So then what happens to the determinant?
0.
0.
The
0.
determinant becomes 0. Right? It means what? Whenever there is a row or column which is a linear combination of the other row or columns, then the matrix determinant is 0. Okay? Okay, this is something which we have as an application of row reduction here. You understand? So it means,
Ma'am, please repeat last concept. Like you are saying determinant becomes 0 after that.
okay, see, when the determinant of this matrix becomes 0, the determinant of this matrix is also 0. That is that you understand, right?
Yeah, ma'am.
So, yeah. So the original matrix determinant is 0. So if this determinant is 0, you know that these three, let us call this to be V3. So these three vectors V1, V2, V3 are linearly dependent. That you can understand, right?
Yes, ma'am.
So it means what I'm saying is that suppose you have three vectors, okay, and one of them is a linear combination of the other two, then that set is always linearly dependent because of this property we get from row reduction. Got it?
Yes, ma'am.
Okay, let me repeat this statement for everyone. Suppose you have a set of vectors where one vector is a linear combination of the other vectors or some of the vectors from the set also, then you can see that that set of vectors is always linearly dependent. I'll write the statement. If there is a vector in a set, let us call the set to be S, which is a linear combination of some vectors in S, then the set of vectors in S is linearly dependent. Clear? Yeah? All right, right?
Yes, ma'am.
Yes,
Okay.
ma'am.
Yes, ma'am. Yes, ma'am.
Okay, fine. Okay. So now look at this question. You all can answer because we have already seen most of the concepts required to answer this question. Read the question. Let S be a subset of R3 which is linearly dependent. Okay, this set is linearly dependent. Now, which of the following options are true? I am adding a vector to this set S which is already linearly dependent. So this set is a superset of S. So is this linearly dependent or not?
Yes.
Yes.
Yes,
Right?
ma'am.
Yes, ma'am.
So this is
Yes.
a superset of S. So this is a superset of S. And we have already seen superset of a linearly dependent set is linear. So this is true. Now S union B must be linear. Yeah.
Yeah. How it is the
Yes.
superset? Can you explain?
Because S is a subset of this set.
S is the subset of the set. Yeah.
Yes, that is why it is superset of S. Okay. So I guess you did not see this part carefully. If A is subset of B, then B is a superset
This
of A.
thing, yes, this thing I understood, but here I am just confusing how.
See, S is a smaller set. Now I am adding another vector 100 to this set. So it is obviously a bigger set, right?
Yeah, right.
Okay. So here I am having 100.
Yeah. Okay, ma'am.
Okay. So this is a superset of S.
Okay, thank you, ma'am.
Okay. Fine. Now S union V must be linearly dependent for any V in R3. Is it not the same?
Yes. Same.
Yes, ma'am.
only, right? Instead of this particular vector, some non-zero vector or even zero vector is also there. Then also we know that it is linearly dependent, right? Okay. Now I am removing one vector. Look at this carefully. Now I am removing one vector. Is this now will the set be still linearly dependent?
It will depend, ma'am.
It depends on the scenario, right? Let us look at two possible scenarios. So let us take the set S is equal to 1 1 1 0 1 0, or maybe I'll take 1 0 0, simpler case. Okay, and then 1 1 0. Now let us say this is V1, this is V2, and this is my V. Now what is S minus V? Is simply V1 and V2, right? Yes or no? And
Yes, ma'am.
about what? Just look at this and tell me the relation between V and V1, V2.
Linearly dependent.
Yeah, exactly the relationship.
A linear combination V1 plus V2.
Yeah, V equal to V1 plus V2. So you see that V is a linear combination of V1 and V2. So you see that this set is already linearly dependent, right? Now I am removing this vector. So I am left with only V1 and V2. Now what can you say about V1 and V2? Are they linearly dependent? If there are only two vectors, it is very easy to check linear dependence. What is the method? Check whether they are.
Determine. Huh?
No. Only when there are two vectors, what is the method? Check whether they are
We are lying on the same line.
yeah, whether they are scalar multiples or not. Can we write one of them as a scalar multiple of the other?
No.
No, ma'am.
No, madam.
In that case, you can say that V1 is not a scalar multiple of V2 for any alpha. So these two are linearly
Independent.
not linearly dependent. Okay, for now I have not introduced linear independence, so not linearly dependent. Okay, so V1 and V2, they are not linearly dependent because they do not satisfy this condition. Okay, so you see that in this case we got that this counter example for this S minus V need not be linearly dependent. Okay, but what will happen if I am removing, maybe if I take another set? It depends on the correct particular choice of set you are taking. You should choose the correct choice, otherwise it will not satisfy. Okay, suppose I am having 1 1 1 2 2 2 3 3 3. Now if I'm removing any one vector, will the set be still linearly dependent or not?
Yes.
Yes, ma'am.
Yes.
Dependent, ma'am.
So this is linearly dependent, and S minus V. So maybe I will write this is V1, V2, V3. Any of this V1, V2, V3, that will also be still linearly dependent only because all are scalar multiples of each other. So we have to choose the correct choice to say that this statement is incorrect. Okay, fine. So it
Yes, ma'am.
depends on the scenario. What is your S and what is your V? Okay. Fourth option, there may exist some V in S such that S minus V is still linearly dependent. There may exist. So they are not saying there will exist, there may. So it is possible they are saying. So is it possible or not? That is what we thought.
Yes, ma'am. This is the example.
Right? Okay, fine.
Yes, ma'am.
Yes, ma'am. Yes,
Okay.
ma'am.
Okay. So obviously the next concept is linear independence, which is the opposite of linear dependence. So what is linear independence? So let us go back to the scenario here. When we have two vectors lying on the same line, those vectors are linearly dependent. Now can you rephrase it for linear independence? What should be the rephrasing? It should be opposite of this.
They are not in the same line.
That's all. In R2, at least in R2, this is the meaning. So when you have two vectors which are in different directions, you have to say or on different lines, then they are linearly independent. This is for R2. Okay. So let us try to understand it with the usual definition. Okay. So in R2, what can we see? In R2, suppose you are having two vectors in lying along different line. So this is V1 and this is V2. then you know that V1 is not equal to alpha times V2. This means that V1, V2 are linearly independent. Okay, linearly independent. Okay, so it means what? One cannot be expressed using the other.
Ma'am, what about the negative direction?
Negative direction, they will still lie on the same line. You just have to multiply with the negative scalar. Right?
Yes, ma'am. Then they will be linearly dependent, ma'am.
Yes. As long as they are lying on the same line, okay, V1 and V2 are not on the same line. This is
Yes,
the
ma'am.
important thing. Okay, fine. Okay.
Yes, ma'am.
Now the definition should be just the opposite of this. So in this definition here, you had the important word here we had is this part. So not all zero is the part we wanted. So what is the opposite of not all zero? All zero.
All zero.
Every
All
zero.
zero.
Every zero.
So all the coefficients must be zero. That's all. So whatever combination you take, like this linear combination you take, so that equation has the only solution given by ai equal to 0 for all I. So this will be the only equation, so only solution for this homogeneous system. Ax is equal to 0 should imply x is equal to 0. Okay, fine. So if a set is linearly independent, then the only linear combination of these vectors that can yield the 0 vector is when all the coefficients are 0. Okay, so now let us start with one single vector. Okay, if V is any non-zero vector, we did not do this for dependent vectors. So let me maybe do this for a dependent case also. Suppose V is equal to 0, then what happens? I'm just considering this vector. Is this set linearly dependent or independent?
Vector have no zeros.
Independent.
Independent, ma'am. Only one.
Independent.
Okay, so the thing is that I'm taking CV is equal to 0. Do I have a non-zero solution for this or not?
Yes.
Yes, ma'am.
Why you are
Infinite solution.
linearly independent? Right? There exists C not equal to 0 such that CV is equal to 0. It means what? It means V is equal to 0.
Linear dependent.
Yeah, this is linearly dependent. So if you consider just a singleton 0, it is linearly dependent only. Okay. In fact, you can get this from this statement also. You should have got this from this statement also. Any set containing the 0 vector is linearly dependent. We already know that. Okay. Even if it is just the 0 vector. Okay.
Ma'am, here also the all the coefficients are zero. Then why this is not linearly independent?
No, I have non-zero coefficient here. V is 0, so C can be non-zero, right?
Okay, yes, ma'am.
Okay, fine.
Okay, yeah.
Okay, now V is any non-zero vector. Okay, now we are in a different scenario. V is non-zero. Now, is this dependent or independent? Now you are having this singleton vector which is non-zero. Is this linearly dependent or independent? So what is the solution for CV is equal to 0?
Oh, C has to be 0.
Yes, 0.
Right? So it means this is the only possible solution. Now tell me, is it linearly dependent or independent?
Li.
Independent, ma'am.
Independent.
Linearly independent. All right.
Ma'am, can you repeat once more?
Okay. See, you are having a non-zero vector. Now, what is the solution for CV is equal to 0? So, what are the possibilities for C? So that C times of V is 0. V is non-zero. So, we need to multiply 0 to get the RHS to be 0, right? So, the only possibility is C is 0. So, if the only solution is 0, then we know that the set is linearly independent. All right? Clear?
Yes, ma'am.
Okay. So two non-zero vectors are linearly dependent if and only if they are not scalar multiples of each other. Is that already known to you?
Yes, ma'am.
Right? We just saw that two non-zero vectors are linearly dependent if and only if they are scalar multiples of each other. Now we are rephrasing it for independence. That's all. Right? Okay. So this is already known to you. So V1, V2, they are linearly independent if and only if V1 is not equal to alpha times of V2 for any alpha. Okay, I'm just rephrasing it. Okay, what can be
Alpha not equal to 0, na ma'am?
see for even for alpha equal to 0, that should not satisfy. That is the scenario here.
Yeah, that is already not equal to.
Yeah, already not equal to is anyway there because you have non-zero vectors, so it is already there anyway. Okay, fine. What can be said about the linear independence of three non-zero vectors? So you have three non-zero vectors. So for two non-zero vectors, we have given a condition. Now, what can you say about three non-zero vectors? This also you know.
Ma'am, in R2
In the
space?
same conditions.
Okay, first let us try for R2 maybe. In R,
Linearly dependent.
The
it
same
is
condition. They are
linearly
not in the
dependent, but
same
what
line.
is happening there? So let us say you are having V1, V2, V3. First, let us consider the case when you are having in R2. What is that you know? This set is
Linearly dependent.
linearly dependent. So if it is linearly dependent, what can you write? At least one of them is a linear combination of the other two. Yes or no?
Yes, yes.
Yes.
This, let us assume this is the case V3 is A1 V1 plus A2 A2. Okay. So it means in R2, if we have linearly dependent set, we know that one is a linear combination of the other two. So the same is the scenario for any three non-zero vectors. Okay. So if you are not able to write any of the vector as a linear combination of the other two, then the set will be linearly independent.
Independence.
Okay. So if you are having any three vectors v1, v2, v3 from Rn, okay, such that none of the vectors, none of the vectors or is a linear combination of the other vectors, then this set S is linearly
Linearly
independent.
independent.
Okay, clear? This is the condition when you have three vectors. Okay, so this is in fact for Rn, for any n. Okay. Okay, so look at this options here. Choose the correct statement. So even before looking at this set, just observe this set. What is that you can see?
Zero vector is present.
It's not a scalar multiplication of one.
First thing you should observe is that the set contains the zero vector. If a set contains the zero vector, what do you know?
Dependence.
Linearly dependent.
Independent.
Linearly dependent, right? So the first option is obviously incorrect, irrespective of whatever is given here. Okay. Now look at the next option. You have now three vectors from R2. Three vectors from R2. Even now also you don't have to look at this expression here. So if you have three vectors in R2, what do you know already?
Linear dependent.
Nearly
A linear combination.
Dependent, right? And also this equation is anyway correct, but you can see that
Ma'am,
this.
please explain option 1.
Okay. So this set contains the zero vector. We have already seen that any set containing the zero vector is linearly dependent. I don't know where I have written that. Where is that? Where is that? Yeah. Any set containing the zero vector is linearly dependent. Okay. So you can see that this set is linearly dependent. And this also we have already seen any set of three vectors in R2 is linearly dependent. Okay, now answer this question. What about any set of five vectors from R2? What
Linearly
about,
dependent.
right? Okay, fine. What about option 3? So just look at this set. So you have now only two vectors. So this is V1, this is V2. Are they multiples of each other?
No.
No, ma'am.
If they are not multiples of each other, then you know that V1 and V2 are
Independent.
Independent. Linearly independent.
Independent.
But here it is given that it is dependent, so it is incorrect. Correct? All right.
Yes, ma'am.
Ma'am, please explain option 2 again.
Option 2. Option 2, here you see that there are three vectors. So first of all, you see that this is v1, this is v2, and this is v3. And v3 is a linear combination of v1 and v2. This is one thing. So you can say linear dependent. But even without this, you know that this set is linearly dependent, because any set of vectors which contains three or more vectors in R2 is linearly dependent. This statement also I have already given to you. So where is that? So in general, any n plus 1 vectors in Rn are linearly independent. In this scenario, here you have three vectors in Rn, R2. N is 2 here.
Okay.
Fine?
Yes.
Okay. Okay, look at this question. If vectors v1, v2, v3 are linearly independent, find alpha plus beta plus gamma. You should answer quickly just by
0.
exactly.
Zero.
Why? All the
No.
vectors, all the
Coefficients are
coefficients
zero.
are 0. So since the linear independence condition is there, that implies that alpha, beta, gamma are 0. So alpha plus beta plus gamma is 0. Right? Okay. This is a straightforward question. Okay. So let S be a solution of a system of homogeneous linear equations with three variables and three equations. Okay. So A is a 3 by 3 coefficient matrix and X is this vector. Choose the correct options. V1 and V2 are in S. So what is S again? So S is the solution set. So it means what? This S is nothing but the set of all X such that Ax is equal to 0. Okay, fine. Okay, now if V1 and V2 are in S, then any linear combination of V1 and V2 will also be in S. True or not? This is the
Sure.
very first example we saw
Yeah.
for week 3, right?
True.
So you know that this is true because you know that AV1 is 0, AV2 is 0. So A times of A1 V1 plus A2 V2 is equal to A1 AV1 plus A2 AV2, which is 0. So you see that A1 V1 plus A2 V2 belongs to S. Okay? Is this fine? Okay.
Yes, ma'am.
What about option 2? The set S will be a subspace of R3 with respect to usual addition and scalar multiplication as in R3. So for subspace, first of all, it should be a subset of R3. Is it a subset of R3? Yes.
Yes.
Yes, ma'am.
Is it closed under scalar addition, vector addition and scalar multiplication?
Yes.
Yes, ma'am.
So it should be a subspace, right? These are conditions for subspace. Yeah.
Ma'am, can you repeat option 2?
See, first of all, for a subspace, it should be a subset of R3. That we have clearly. And we also should have the condition that S should be closed under vector addition and scalar multiplication. That also we have already seen. It follows this similar way of verification, that it is closed under addition and scalar multiplication, right? So if this set satisfies all this condition, then we know that it is a subspace of R3. Correct or not? Yeah.
Okay.
Fine. What about option 3? The set V1, V2, V1 minus V2 is a linearly independent subset in S.
Ma'am, it's given dependent.
Sorry, linearly dependent subset in S. So you
Yes.
see that V1, V2 suppose in S and V1 minus V2 is a linear combination of
V1 and
V1
V2.
and V2.
V1 and V2. So if a set contains a linear combination of the other vectors, then you know that that set is linearly
Linearly dependent.
dependent. Okay. The set V1, V2 is linearly independent subset in S if V1 is not a scalar multiple of V2.
Yes.
Yes.
Yes, ma'am, it's true.
So far everything is clear, right? Yeah.
Ma'am,
Yes,
I'm
ma'am.
confused about the question, ma'am. I didn't get what exactly the question is asking.
Just choose the correct statements
Uh,
about the.
no, ma'am. The question statement, let S be a solution set of a system of homogeneous linear equations with three variables and three equation
Hmm.
whose matrix representation is Ax is equal to 0.
Yeah.
I'm confused about when you say solution set.
Mm-hmm.
Uh, then yes, we are talking about the vector x. So how come it is a set? I'm confused about that.
Is this a set or not? Whatever I have written here, is this
Yeah,
a set?
ma'am. But I think shouldn't it be a single vector or will
See,
be?
what is the solution depends on your a, the values of a. So it can be a singleton set, or it can be if it has infinitely many solutions, then it is an infinitely many infinite set, right? Yeah.
Uh, Ma'am, for a given matrix A,
Mm-hmm.
the values of x will be, let's say, if I'm having an x, okay, it will depend upon number of solutions. Yeah, true, ma'am. Got it, got it.
Okay. Fine. Okay. Okay. This also everyone should answer right after reading the question. How many vector? First of all, read the question. So you have V1, V2, V3, V4 from R3.
R3.
So what do you know already about this set?
Linearly dependent.
This set is linearly dependent because there are four vectors from R3. So it is linearly dependent. So how many values of A can make it
Infinite.
linearly independent?
Infinite.
Infinite.
Yeah, ma'am.
This set is linearly dependent already.
Mm-hmm.
So the question is for what values or how many values of A will make this set linearly independent?
Oh, independent. Zero value, sorry.
Yeah.
I
So
thought it was asking linear dependency.
there are no values of A which can make it linearly independent. Okay. For which V1, V2, V3, V4 is linearly independent. Clear? Yeah.
No,
Yes,
ma'am.
ma'am.
No values.
See, even without knowing what is the value of A, we already know it is linearly dependent. Whatever value you put for A, you still have four vectors from R3. So it is not going to change the linear dependence of this set, this vectors. So it means you cannot have any A for which this set becomes linearly independent, right? Yes or no?
No, ma'am.
No, you did not understand.
No.
See, let us say you have some specific value for A. How many vectors still you will have?
3.
3. How many vectors are you having here? 1, 2,
Oh,
3, 4.
4.
So if whatever you put
But
for
ma'am, how there is no value for which this is linearly independent?
that is what I am telling. Whenever you have four vectors from R3, you already know it is linearly dependent. So whatever value of A you put, you will still have four vectors from R3 which will make the set linearly dependent only. It can never be linearly independent because there are four vectors from R3. That is the condition I just told here also.
Yes, ma'am, that is clear. Like this set is linearly dependent.
Mm.
But you have written we can't find the value of A.
Yes, there are no values of A for which this set is linearly independent. This
Okay,
set,
okay, ma'am. Okay, okay.
okay,
Okay.
okay, okay. So this is based on your understanding. Let's see how far you have understood. Choose the correct statements. So union of two distinct linearly independent set may be linearly dependent.
Yes, ma'am.
no,
You
ma'am.
can.
True, true.
True, right? For example, let's say you have 1 comma 1. This is a linearly independent set because we know that any non-zero singleton non-zero vector is linearly independent, right? So this is linearly independent, and 2 comma 2, this is also linearly independent, but the union,
Linearly dependent.
Dependent.
yeah, so A union B is linearly dependent. Okay, this is true. Union of two distinct linearly independent sets must be linearly dependent. Must be linearly
False, ma'am.
dependent.
False.
Right? Again, you can take 1 0 0 1. Now you see A union B is linearly independent.
Independent.
So this is linearly independent, this is linearly independent, and the union is still linearly independent. So this is incorrect. Non-empty intersection. Yes. Any questions? Okay. Non-empty intersection of two linearly independent sets must be linearly independent. Now we are talking about intersection. Non-empty intersection of any two linearly independent sets must be linearly independent. Is that true or not?
True, true.
False. False.
Think again carefully. We are talking about, see, intersection means it is a subset of linearly independent set. So think again carefully.
So, ma'am, it's been said
True,
that
ma'am.
it has to be non-empty intersection. So there will be at least one vector,
Yes.
and it has to be linearly independent.
Yes. See, what happens is that just like we saw that any superset of a linearly dependent set is linearly dependent, we also have the statement that any subset of a linearly independent set is linearly independent. True or not?
True, ma'am.
True or not? Right? So this is also easy to verify, right? So suppose you are having a set V1, V2, Vn. Suppose this is linearly independent. Okay, now I am taking any subset. Okay, any subset of this set. Okay, so this is a subset of, let us say this set is. So this is subset of S. So now if I take A1, V1 plus etc. AK, Vk equal to 0. So what do I know? I can only have AI to be 0 for all I. If I'm having non-zero coefficient, then I will have non-zero coefficient here as well, and the set will become linearly dependent, right? So
Yes,
this
ma'am.
means that any subset will be linearly independent. So now intersection, suppose you are having two set, okay, and the intersection is non-empty. It means what? This set S1 intersection S2 is a subset of S1 as well as S2, right? Yeah.
Right.
So this is the intersection part. This is a subset of both. So we know that subset of linearly independent set is linearly independent. So this is
True.
all right.
Yes, ma'am.
Okay. Non-empty intersection of two linearly independent set must be linearly dependent, which is
False, ma'am.
False.
okay. Okay. So this is important thing, which kind of this question I added because it kind of summarizes whatever we have studied about this system of linear equation and the solutions. So you have the vectors given to be linearly dependent. Okay, if the vectors are linearly dependent, first already you know something about this matrix A, which contains these as the columns or rows. So what do you know about the matrix A?
Determinant will be 0.
Yes.
Union 0.
So since this is linearly dependent, you already know that the determinant of A is 0. This is the first thing you should know. Okay. So now you are having some system of linear equation. Okay, and this is the matrix representation. Now we have to look at the options here. Either the system of linear equation has a unique solution or no solution. What is your take on this?
Ma'am, infinite solution must be there. Determinant 0, na?
Determinant 0, but is there not a possibility of no solution?
Yes, ma'am.
Ma'am, we'll be having one row or column entire 0 in this case.
Yes.
So
See, Already we know that only possibilities are no solution or infinitely many solution. These are the only possibilities when determinant of A is 0, right? For this system,
Yeah.
these are the only possibilities, but they are saying it has unique solution or no solution. But we have infinitely many or no solution. This is the correct combination, right? Not unique solution or no solution. Right? So this is incorrect. What about option 2?
Correct, man.
Correct.
Right.
Okay. Either the system has, and now again the combination is incorrect. Infinitely many or unique. Unique cannot happen. Right? Unique cannot happen. So this is again incorrect. The system of linear equation has a unique solution. Again, it is incorrect. So is the matrix invertible?
No, man.
No, ma'am. Determinant 0.
Okay. That's all. Okay. So this is something which everyone should know. So just with this vectors to be linearly dependent or independent, you can guess the solution how it can be from the for the system of linear equation. Okay, so this is a very important thing about the relation between linear independence and the existence of solution for the system which contains the vectors as the columns or rows. Okay, so finally I have just summarized the things I have told. So what are the ways of checking linear independence in R2? So if it is a zero vector, what do you know?
Dependent.
It is linearly dependent. If it is a non-zero vector, what do you know?
In R2, only one vector or more than one vector?
One non-zero vector.
Linear independent,
Then
then
linear
non-zero vector. Yes,
independent.
Suppose two vectors in now we are in R2. So if you have two vectors, there are two ways to check. Of course, the first method is scalar multiple method. So here, if you are having two vectors v1 and v2, and if v1 is alpha times v2, you know that v1, v2 are linearly dependent.
dependent.
And if it is not scalar multiple, then you know that they are not linearly dependent, they are linearly independent. Now suppose you have them in this form as a matrix, and if you find the determinant to be 0, then again it is linearly dependent. So all this is for linear dependence. So the same opposite conditions will give you linear independence. So for two vectors, how to check linear independence, is that clear?
Yes, man.
Suppose there are 3 or more vectors in R2.
Dependent.
Always dependent.
Yes.
Always dependent.
Now in R3, what about the 0 vector?
Linear dependent.
Linear dependent.
And one non-zero vector if you are having?
Independent.
Linear independent.
If you have two vectors, you have to use the same scalar multiple method only. If v1 is equal to alpha v2, then v1 v2 are linearly dependent. Okay. Now if you have three vectors, you have to use the determinant method. So if determinant v1, v2, v3 is 0, then this set of vectors are linearly dependent. And 4 or more vectors?
Dependent.
Linearly.
Always linear dependent.
So more generally,
Yes.
if you have k vectors in Rn where k is greater or equal to n plus 1, that set is always linearly
Dependent.
okay. A set
Dependent.
containing a zero vector is always
Dependent.
Dependent.
a superset of a linearly dependent set is
Linear dependent.
Dependent.
linearly dependent. Subset of a linearly independent set is
Linearly independent.
Dependent.
okay. So I have just
Why do they say that if the set only contains the zero vector, still it is always dependent?
I have explained it already.
Yes,
Any
because confirm that there is a
any coefficient will lead to that equation.
Okay, the coefficient will automatically be 0. We can easily find a non-zero coefficient for the zero vector. Right?
Right.
Okay.
yes, madam.
Okay, fine. So just the final thing. This is also just summary only, nothing new. So if you are having a set of n vectors and you want to check whether they are linearly independent or not, what is that you can simply do? So let us say these are your vectors, v1, v2, vn are the vectors. So this is the equation you will consider first of all. c1, v1, c2, v2, plus etc. Cn, Vn equal to 0. Now let us say your Vn, V1, V2, Vn are vectors from Rm. Okay. Then each of these vectors can be written in this form. So your equation will be like this now. Okay. So now you can rewrite it in the matrix form. So in the matrix form, you have A times of x is equal to 0. So now checking the linear dependence or independence of the system becomes a problem of solving this homogeneous equation Ax is equal to 0. So what you should know, first of all, how to find the what are the possible scenarios for the solutions of Ax equal to 0. Only if you know this, then only you can answer this. This is the fundamental. So I just want to brush up on the fundamental part, quickly answer this, and then we'll wind up. So homogeneous system Ax equal to 0. This system is always consistent.
Okay.
And what is always a solution?
0.
Yes.
0 is always solution.
A square determinant of, and if determinant of A is non-zero, then the system has
Unique solution.
unique
solution.
Unique solution, yes, ma'am.
And if determinant is 0,
Infinite.
Infinitely many solutions.
Infinite solution.
okay. Now suppose we are in the rectangular system. That is, we are having an m by n matrix.
Ma'am, we can see no solution also, na?
Just now we see that
That
it is
is not
consistent all
inspired.
tokens.
Okay.
A is rectangular. A is an m by n matrix. So what is m and n representing? Which is representing equation and which is representing the variables?
N is variable, M is equation.
Yes, this is the number of variables and this is the number of equations. All right. Now, if m is greater than n, then the maximum value of rank of A is. So we did not introduce rank yet, right? The rank is not yet introduced. But anyway, so this is what we will be using later. So, okay. So maybe I'll just say that if m is greater than n, then you have two possibilities. Okay. So let us now just consider this part. If m is greater than n, then either you can have a unique solution or you can have infinitely many solution. Okay. But if m is less than n, we have already seen this scenario today. Right? If m is less than n, you will definitely have independent
Infinitely many solutions.
which gives as infinitely many solutions. So this is what you should know about the solutions of Ax equal to 0. So only if you know this, then only you can answer the independence part. Right? Okay. So I have given two homework questions here. So just checking the...
Ma'am, please explain third bullet.
This one?
Yes, ma'am.
See, I have already explained it. So I explained it with a 2 by 3 matrix. So suppose let us say you are having a 2 by 3 matrix. Okay. Then obviously your REF form is something like this, or it can be something like this, right? So anyway, you will have an independent variable. So here this will give you an independent variable. And here this will give you an independent variable. So whenever you have an independent variable, that independent variable can take any value, right? Yeah. So it means you have infinitely many solution. Yes or no?
Yes, ma'am.
Okay, fine.
Ma'am, in case 2, here m is the number of equation. In matrix, m is the row or n is a column. Means row is the equation or column is the variable. Like
Tell me, m is row or column?
m is the row.
N. So m is the equation.
Okay, row means equation. Okay, ma'am, got it.
If you have any kind of some doubt like this, just
Yes.
take an example. See, for example, you take a 2 by 3 example. Just quickly convert it into system of equations and just find it. Okay. So this kind of things you should quickly verify with an example if you have some simple doubt like this.
Yes, ma'am. Thank you.
Okay, fine.
Yeah.
Okay, so that's all for today. I hope you all understood today's session. Yeah.
Yes,
Ma'am, will
ma'am.
this PDF be available?
Sorry, someone is asking something. What's that?
Ma'am, will this PDF be available, ma'am?
Of course, as usual. In the
Ma'am,
drive.
ma'am,
Yes, yes.
do we need to make notes for this because there are a lot of recording lecture along with this, and also TA session.
Okay.
So how to make notes, because
already
there are
have
a
the
lot of
notes
things.
with you already have the notes with you, so there is nothing to make separately. This is sufficient. Suppose you have some doubt somewhere and you are writing further clarification, you can just add your explanation to understand that part in this same PDF itself. You don't need to prepare separate notes. That is my opinion. Okay, any other questions?
But in the end, ma'am, there will be a lot of PDFs. How in short
Of
span
course,
of time we can
that is
get
what
a
you